Today, we will revise organic chemistry, and it seems like there are a lot of topics, but you will see there are not. And I'm going to highlight mostly the basic concept of organic chemistry, because if you know the basics, then trust me that you can work out any mechanism. Okay, so the first step is to have clear all about organic chemistry. So I'm not going to focus on this too much, but it's important that you distinguish between, hydrocarbons, branched chain, linear chains, okay? Because in the exam questions, these are the keywords that will help you in, for example, when you have to work out a structure from either spectroscopy data or just the organic test, and you have to draw the structure, you must notice these things like, is it a linear? Is it branched? Is this a cyclic molecule? Is it a linear molecule? Okay, so homologous series, to be honest, is not the most useful thing, remembering the general formula. It is useful, I think, as far as we go to like alkenes, alkanes, alkenes. But as we go to further functional groups, don't memorize the general formula, but just work it out. Okay, what I ask you to be 100% confident with is the different type of functional groups and what they look like, because like this, you can always write down like one molecule and then work out the general formula from it. Okay, one point that I want to highlight, you do need to remember the type of formula, because of course there are depending on what you're asked in an exam question, you should use different formula. For example, molecular formula, empirical formula, they're very distinctive calculations like the ones that we started this lesson with. Displayed formula is the one that shows all the bonds, which is exactly this one. Let me put a highlighter there, actually, is this one. But this, I think it's useful, for example, when you have to show isomers, compare different structures, but maybe mechanisms, but it's very limited because it takes too long. We don't need all of these hydrogens. Skeletal formula, though, it's a lot more useful when you have to quickly work out on a paper like the mechanism, or you're trying to play around with the structure, for example, in working out isomers. So I would rather you get confidence with the skeletal formula than all the others, because at the end, the displayed tells us the same thing, but this is just simplified. Yeah, every corner being the carbon. The structural formula, we can write it in both these ways, and this is actually the most useful one when you write chemical equations, because we still have a good idea of the structure, yeah, but in a way that it can be just an equation, reactant to products. Okay, so please practice this in their different contexts. The functional groups, you need to know them, of course, but don't stress out too much if you don't memorize them right away. You will, the more practice you get in organic chemistry, the more familiar you will be with the functional group. Okay, if you're now in year 13 at the end of the year and you still are not confident with all of the functional groups, the best way to do is make some flashcards, name and the type of functional group, and keep testing yourself, because if you don't have the memory at the end of year 13 of the functional groups, you need to work on it. If you're in year 12, don't worry, it's just good to have a list, but you will get confident with time. Naming. So I would still go through my method of naming because I think it's nice and concise. So it's good to have a revision and remember that if you are asked to do a UPAC nomenclature in your A-level papers, it's not going to be an easy one. So if you can simplify it, I think it's better. So remember, the name is prefix, chain, and suffix. Prefix always tells us the chain length, which means that this is really the first step when you want to name a molecule. Find the longest chain. Then the type of the chain, if it's an alkane, alkene, and alkyne, this is the suffix that we add. And notice that the very last letter, it's the suffix. So this is the functional group, okay? Depending on the functional group, a different suffix, okay? And then this is the main chain of the name. But then, of course, there are many other steps. We needed to check if there are side chains, check if the functional group can be in different positions, and if there is more than one chain, the number. So you're building up this name from the main chain, and then you add the side chain, the number of the functional group, and then the multiple prefix if there are any. Okay, so I would suggest you to really build up the name in different ways. A-level students, amino acids is this example where you have this a little bit more difficult naming to do. Still go back to basics, okay? You cannot forget di, tri, tetra, penta, or whatever, or to number the functional group. I'm not allowing you to forget in year 13. So go back to basics to build up the name, even though, yeah, it's a more complex molecule. Another mistake that I don't want you to make is the number, is the punctuation. Numbers are separated by a comma, like this, butan 1-2-diol. Letters and number are separated by the upper score. I know it's confusing, but this is the rule. Okay? I'm not allowing you to get this wrong. So please have it clear. Okay. Year 12 students, if you don't know exactly how to practice naming, you can combine it with practicing isomers, because doing isomers and naming together is a super nice way to combine the topic. Now, doing a little revision of isomers, because you will come across this in transition metal, yeah, for year 13 students, and well, we go into a bit more complex isomers also in year 13, which will be the optical isomers. But anyway, that's for next year. But if you're asked as well, this type of question is going to be a challenging one. And one challenge is in these more open questions where you have to work out the structure and you're given a hint of the type of isomer that this is. So let's go through the basics. Definition of isomers: molecules with the same molecular formula but different structure or arrangement in space. Important: structure or arrangement in space, because we have structural and stereoisomer. The different structural arrangement is the different structure is the structural isomer, of course, and stereo would be the different arrangement in space. Now, structure, we have chain, positional, and functional group. Chain isomer, different carbon chain, you can just chop it up and then name it differently. Positional, check if the functional group can be different positions. And of course, if the name is different, it means that it's a different molecule. Functional group isomer is the trickiest one to work out. So we're going to look at some examples, because also year 13, this is an easy one to forget. Then geometrical isomers. Alkenes, yeah, they have different groups around the double bonds. You have to remember this, because when you have, for example, one of these open questions where you have to work out the structures, like even in NMR questions, if you have this, like it can be a geometrical isomer, it should click straight away that it's an alkene. Okay, so we will see in the more complex exam questions. And then opticals, different carbons with 4 different groups attached, because we know the shape of carbon is tetrahedral. 4 different groups, it will be a specific type of isomers, okay? But we won't go into detail in that. Now, the one that I want to highlight is the functional group isomer. The ones that I would highly suggest you to remember are alcohols and ethers. As you can see, is just the oxygen that it's moved in between the chain. This is even more important: alkenes and cycloalkanes, ketones and aldehydes. Okay, so those are the key ones. I'm gonna pause 1 second. Okay, no, never mind. I'm not gonna pause. If there is one more example that is not written here, but I hope you're thinking about it, and I'm gonna write it like this: carboxylic acids and esters. Okay, carboxylic acid and esters, they're also functional group isomers of one another. Okay, so I hope it's clear. Now, we're going to look at the basics of mechanisms. I'm going to 1 second stop sharing here. Okay. This could be the most important part of organic chemistry that you study, and it's mechanisms. So mechanisms, of course, they show bond breaking and bond making of organic molecules, okay? It's all shown through these curly arrows, which is movement of a pair of electrons. You must fully understand and visualize the pair of electrons moving as you do the mechanisms. Because if you visualized it, you won't have to memorize any mechanism, but you can always work it out. And you will not miss intermediates like positive, negative charges here and there, or have the wrong number of bonds, because you really visualize the movement of pair of electrons. Okay, we will get into that a little bit more, but just the two types of fissions. So remember, fission means breaking. Homolytic and heterolytic. Homolytic, you're not required to know any mechanism of it. However, I suggest you to just look at it, just to understand the free radical mechanism, okay? Because it just makes it easier to visualize the free radical substitution. So homolytic, even breaking, homo, even. Heterolytic, uneven breaking of covalent bonds form ions, okay? So notice that the pair of electrons have moved onto the chlorine. Now, I want you to really visualize why are there charges present, okay? And here you need to remember the dot and cross diagram, really as simple as that. So carbon has 4 electrons, right? But now carbon has 3 electrons because a pair of electrons has moved away, right? Chlorine is sharing 1 electron, but now as the pair of electron has moved onto the chlorine, notice how it has 1 more electron, okay? It's not obvious. You must be able to observe, yeah, and to visualize these, you know, this dot and cross diagram of the molecules, okay? Trust me that this will help you in the exam, because I don't want you to work on memory. It's unreliable. I want you to really visualize everything and kind of be more conscious as you do every question and mechanism to prevent any type of mistake and so on. Okay, so looking at the mechanism, the second most important thing to remember is that it's always nucleophile to electrophile. Nucleophile, nucleus loving. It's an electron pair donor. Here we have the main examples you will see: hydroxide ions, cyanide ions, ammonia or any with amine, and an electron reach, so the carbon double bond. Electrophile electron pair acceptor, we have carbocations, positive dipoles, so check the dipoles, remember how to work out dipoles, so basic of or electronegativity, okay, and electron deficiency that you will see in when you do benzene and you look at the halogen carrier. If you A-level students, try to visualize it with me. AS students, forget about what I'm saying, but imagine if you remember, for example, iron bromide with the bromine molecule that carries, you know, the bromide. Why can it do that? Because it's an electron deficient. I hope you're visualizing it, okay? Just to notice how the basic are, you know, recurring in the more complex topics. Let's look at a summary of all of the mechanism types. I know it's a lot to take in, but I just want you to be able to observe this because it's important. So addition reactions, we will have formation of one single product from 2 reactions. It's not written in here, but also notice that the reactions go forward and backward. Addition is actually the reverse of this reaction. Elimination, removal of a small molecule from a larger one, is the opposite of addition. Substitution, replacement of one atom or a group of atoms by another. Yeah, this is the second equation. Hydrolysis, breakdown of a molecule by water. Important to name this, okay? Hydrolysis is the opposite of condensation, which would be, I'm going to write it in green, condensation, yeah, is the opposite of hydrolysis. Oxidation, We now don't worry too much about the definitions of gain of electrons, loss of electrons, but oxidation and reduction in organic chemistry, it's better observed as gain of oxygen, loss of hydrogen. Same for reduction, gain of hydrogen, loss of oxygen. And we will practice a little bit how to write these equations, because oxidation is written with the oxidizing agent this way. Reduction is written as the reducing agent in terms of hydrogen. Okay. And this marks the end of the first part, which is the basics of organic chemistry. Trust me, the most important thing. Now, we will go through some of the key definitions of each functional group, okay, as well as the reactions that you need to know. And then don't worry, I'll try to stay brief. Now, some important keywords in alkanes. We know it's the simplest functional group, but important. Aliphatic, yeah, saturated hydrocarbon. I'm going to highlight this word once again, thinking about these very open A-level questions, 6, 7, 9 marks, where you have to work out a structure of a molecule. These will be the terms that you need to recognize. Saturated hydrocarbons, maximum number of bonds. It pretty much tells us that there is no double bond. Aliphatic, okay, meaning it's this type of molecule that is just not aromatic, okay? Aliphatic is just not aromatic. Aromatic is just benzene, the example that you study in this course. Linear, branched, okay? Once again, important if you have to work out any functional group. One key point, and here I am jumping back to talking about intermolecular forces, that branched molecules have lower boiling point compared to linear molecules. Why? This is how in an exam question you have to explain it, because there are less point of contact between the molecules, therefore lower van der Waals forces. Okay? Normally it's a couple of marks, easy to get if you understand the concept of forces and about, you know, actually if you think about which type of force is it present in this type of molecules, only London dispersion force of van der Waals, because there are no dipoles. Okay, good. So bonding of alkanes. Now, important to be able to define this type of bond, which is called the sigma bond. Sigma bond, it's the first bond that the molecule will form, and it's formed by in 2 different ways. And here I am jumping back into the topic of atomic structure and the shapes of the subshells. S orbitals, they're spherical. P orbitals are dumbbell shape. The carbon molecule is bonding with its p orbital. Okay, and here I invite you to look at the periodic table and the electronic configuration of carbon. Hydrogen, of course, is only the s orbital, and to form the sigma bond, we have the direct overlap of an s and a p orbital, and this is the carbon. If you have done hybridization yet, if you don't know what I'm talking about, just don't listen, but hybridization, sp4 for this type of carbon, because we have 4 orbitals, yeah, that are hybrid between the s and the p orbital. Now, takeaway point, sigma is the direct overlap of 2 orbitals, can be 2s, can be 2 p orbitals, so the direct overlap of the p orbitals, or can be 1s and 1 p orbital. This is called sigma, is always the first one. We will look at alkenes, how these are different. The next part that most of you need to know, but it's just GCSE revision, so I'm not going to go through it now. If you want, you can access the AS Chemistry Crash Course and have a look at the basic concept of fractional distillation, cracking, and the uses of alkanes, okay? But I'm not going to go through it now. Combustion, I hope you are confident in writing down these equations and balancing them, okay? Because I'm not going to go through it now. The first mechanism, not mechanism, but the first reaction that you do need to know, and that it is assessed in a more complex exam questions, is the free radical substitution. And if you know the basic steps, then no matter how difficult the question is, which functional group you have, which number of substitution you have, you can always work this out, okay? free radical substitution. Remember, substitution means taking the place of free radical because we have radicals. Now, free radicals are formed by UV light, and it causes a homolytic fission. Remember, species with unpaired electrons is the definition of radicals. You never know, could be 1-mark question in the exam. And this is how it works. Normally with chlorine, we form two radicals. Now I want you to picture the homolytic fission of one electron going on either side. Propagation step. Now, the thing that I want you to notice is that the first and the second propagation step are always the same. So if you know this, you will always be able to rewrite it. The first propagation step, it's always that, and it's written here. The radical, but I'd rather you observe it in the diagram. The radical takes the hydrogen and it leaves behind carbon radical. Second step, the carbon radical reacts with an initial chlorine molecule or an initial molecule to reform the radical and to form the desired product. This is always the order of the steps. So imagine that in an exam question, you're asked, what's the second substitution? Write down the propagation step for the second substitution of this molecule. Write down the propagation steps for the formation of this specific molecule, even if you have a more complex. Yeah, always look at these steps. Okay, so we can simplify it a lot because at the end it doesn't matter which molecule you're given. The steps are always the same. Okay, termination step. Two radicals joining is called the cleavage. If you hear this word, it's cleavage of the radicals. Now, A-level students, you have done kinetics already. You have done the mechanisms of, first step, second step of like a rate, compared it to a rate equation. And we have some recurring terminology here. The radical, because it's, I'm going to highlight it with a color. The radical, notice that it's used up and then reformed. This is what we call a catalyst. The CH3 radical, it's the opposite. It's formed and then it's used up. This is the definition of an intermediate. Okay? And then notice how, if we put these steps together, we have an overall equation, just like we do in the multi-step mechanism. Okay, notice you studied this at the beginning of year 12, and we do the hard kinetic in year 13. Okay, but it's very similar. Just notice the similarities. Okay, so this is the step that you need to know for alkenes. Now, the extra, the part that is a bit more challenging and that is often assessed in the exam is to write side products or to explain why this is not a useful mechanism. And remember that the way to explain it is that radicals are highly reactive species. There are side reactions that can take place to form a mixture of product or further substitutions. Okay, and here are some examples. Terminations to form like longer chains of alkanes, or we could have further substitution. Notice this is the propagation step of the further substitution. Okay, so this is important to be able to write it down, because if you're asked about free radical substitution in the exam, it's likely to be something like this. Okay, and this is the end for the first part, which is alkenes. I would invite you to review this lesson and go through each of these checkpoints to make sure that you're confident with it. Okay, because I'm going to keep going. Remember, it's a crash course lesson, so it will be a lot. Okay, but you will always get the chance to go and review it. It's just to have the overview and to refresh everything. Now, next the functional group, alkenes, and don't worry, everything gets shorter as we continue organic chemistry because it's just more concise. So general formula, I told you, doesn't matter because you can work it out all the time. Definition, yes, unsaturated hydrocarbon. Once again, if you read in the question, unsaturated hydrocarbon should link to alkene. Okay, double bond. Now, the definition that I want you to analyze a little bit more is the type of bonds that are present. It's a pi bond. Pi bonds are formed by the side-on overlap of p orbital. This is how it's formed. Remember that if you have to show the diagram of p orbital, this is the one. This is shown how it's formed, but this is the orbital, that this is how you are supposed to write it, okay? If you have to describe it, it's a p orbit, or the side-on overlap of p orbitals above and below the sigma bond, okay? Above and below. Now, the consequence of this is a restricted rotation around the double bond. Again, the keyword to explain the formation of geometrical isomers. So if you're asked to explain how geometrical isomer formed, this is what the mark scheme wants you to say. Now, geometrical isomers, there are two different notations, cis and trans and E and Z, and sometimes it's not clear how they're defined, like when to use them, but this is how we can simplify it. Cis and trans are used when only two groups around the double bond are different, so you can compare the relative position. So here are two examples. Trans, the hydrogens are on opposite side. I can clearly see that. Cis, the hydrogens are on the same side. However, you can also use E and Z for this cis and trans, but you can't use cis and trans for E and Z. So E and Z are used when the groups are different and we cannot really compare the relative position. And priority groups are on opposite sides for the E. And this is how to explain it. Priority groups on opposite side. Priority groups on the same side would be Z. Now, the order of priority is based on the MR of the atoms attached. What this means is that you must look at one atom at the time. I'm comparing carbon and I'm comparing oxygen. I'm not comparing CH3 and OH. If that is the same, for example, if I am comparing carbon and carbon is the same, what is next? Hydrogen. Hydrogen too. I look at the atom after. Hydrogen. Hydrogen here as well. So for now, they're all the same. But the other atom that is different will be this one, because the third atom here, it's hydrogen, but here it's a carbon. So these would be priority. Obviously, you're comparing the priority on the same hydrogen. I'm just showing you the on the same carbon, because you need to give the priority around the double bonds 1 and 2, okay? But it's just so to show you how to compare it. So in this case, just let me do this example for you. If we compare carbon and hydrogen, of course, carbon is priority, so this will be our number 1 priority. If we compare carbon and oxygen, not the whole group, my apologies, but carbon and oxygen, of course, oxygen takes priority, so this will be our number 1. Priority groups on opposite side, it's E. Okay? I hope you get it. Otherwise, check in the AS Chemistry crash course for a lot more worksheets and guided explanations. Okay? Now we get to the nicest part of organic chemistry, which is how are you going to study all of the mechanisms, all of the reactions? The best way, I think, is having flowcharts, okay? Have reaction schemes where you can summarize all of the reactions, okay? Now, I'm not going to go through every single condition, because I think it will go in and out because it's just too many, okay? I just want you to notice how I'm doing these notes, okay? Because this is how you, I would suggest you to study them, okay? Doing flowcharts for the type of reactions. And notice the reactions, I mean, we have already mentioned all of the basics: addition, reduction, what do they look like, okay? So I'm not gonna highlight this too much, just you must get the time to either use my revision card or make your own flow diagrams. Okay, in terms of reactions, electrophilic addition is the second mechanism you study, and it's important for these for alkenes. Okay, just a little bit on the basics. Remember, nucleophile to electrophile. Notice that you always have to think about if there is a charged intermediate, which there is in this case, and then the second step. Once again, I've covered the basics of nucleophile, electrophile, curly arrow mechanism. So I'd rather you work out this mechanism in our exam practice rather than now. One point I want to make is to remember this Markovnikov rule, which is a little bit tricky. Now, the important concept to understand here also for actually acid and base topics, amines in A level, you must understand this concept of inductive effect. Now, if you have an asymmetric alkene, the carbocation can be in different positions, okay? Now, the major product is determined by the most stable carbocation. The most stable carbocation is stabilized by what is called an inductive effect. Inductive effect is the donation of electron density through a bond. Alkyl groups are called electron donating groups. You might remember this if you're in A level from our directing group in benzene topic. Electron donating groups. This means that they stabilize the carbocation. So the tertiary is the most stable. The most stable will give you the major product. Okay? It's important to understand this. And why is it more stable? Well, it's more stable because it's the least charged. So let's say that when you have an intermediate that is less charged, then it's more stable. Okay? That's how it is. Okay, so we looked already at two mechanisms, at two key reactions, free radical substitution and electrophilic addition. Addition polymerization, you should remember from just C, I'm gonna just skip through it, even though we would do some exam practice on this because it's important. Now, I am going to go through alcohols. Just some key concepts. Trust me that everything gets shorter now, okay? I won't be too long talking because I want you to get some exam practice too. Alcohols, just like any functional group that we'll see from now on, the classification is fundamental. Primary, secondary, tertiary. Primary, only one group different than carbon. Sorry, only one group is different than hydrogen. Secondary, two groups that are either carbons or different. Tertiary, three groups. Okay, very, very important, the classification. Now, fundamental, and here, wow, this is so important for alcohols and for, we studied intermolecular forces, and you will be asked to explain this, even to write this diagram, sometimes it's the hydrogen bond, okay? Alcohols form hydrogen bond, and this causes a greater boiling point. If you don't remember intermolecular forces, make sure you go and revisit this lesson. But remember that this hydrogen bond between the water and the alcohol is also what determines the solubility, okay, which of course depends on the strength of the hydrogen bond compared to the van der Waals forces. Because if you have a very big carbon chain, it might not be soluble. This is a nice exam question to come up, about the solubility. And if you're asked about the solubility, you are asked in writing down the diagram. And remember, this links back to the application of intermolecular forces and the difference between the different molecules, okay? But this is another topic. Now, formation of alcohols, you will see that a lot of reactions, they overlap. Still, it's nice to have it as a summary because, we saw this in the alkenes. Well, this also is, to form alcohols. That's why to have like a nice flow chart of all of the conversion of different functional group, it's useful to see the overlap. Okay. We're now looking at the third mechanism that you need to know. Okay. AQA students, you're the only one that must know the mechanism. All the others, they just need to know the reagent, which is somehow difficult to remember. Okay. I'm not going to go through the mechanism right now, but we will do it if we encounter an exam question. One tip actually that I want to give you, also so your brain takes a break, is like how are you going to remember so many mechanisms? Okay. Sorry, 1 second. Sorry, I'm texting on the thing, but to the wrong person. So apologies who received the message that it was not supposed to say. Anyway, if someone has to leave because it's all good. The point that I wanted to say, like how you study organic chemistry, these revision cards, they're extremely useful if you take this revision card, you copy down the mechanism in your paper, but copy consciously in the sense that you're writing down, and then every curly hour that you explain and you copy from this diagram makes sense to you, right? And then in the second time, you try to write down the mechanism, you look a bit less at this revision card, and then you move on and on until you're able to do the mechanism completely alone by giving meaning to every step that you do. So it's kind of like a copying from the revision card, but with mindfulness. This is really how you will learn organic chemistry. Okay, anyway, the next part, it's oxidation reaction, fundamental. These always come up in every level paper, okay, sometimes. And if you will be lucky to have it in this level paper, you have a 6-mark question to explain how conditions and reaction determine the product. Remember, primary, secondary, and tertiary, we discussed the classification. Be confident in writing down the equation. Very important to remember the different techniques, distillation and reflux, okay? Remember the definitions. Now, the agents, extremely important, also the colors, because this is not only 2 colors of transition metals that you already remember, but it's also one test for alcohols that you already know. So please remember that. Now, in primary alcohols, very important that you distinguish between distillation and reflux, that you know how to label things and even explain things. One tricky question, it's actually the water in, water out. Why is that? You could be asked. And remember that is because you want to create a homogeneous temperature gradient. While if the water goes in here and out here, you don't have an homogeneous temperature gradient in the reflux. So the same would be for the condensation flask. I mean, the condensation apparatus here. Okay. Then other exam question you can get experimentally speaking, the anti-bumping granules. Okay. Remember that they just prevent too big bubbles to form and spillings. Okay. Then explanation of why distillation and reflux, it's down to the boiling point, and it's all down to hydrogen bonds. Okay, make sure if you have to explain it, this is how. Yeah, they have aldehydes, they have lower boiling point compared to alcohols and carboxylic acid, as they don't have hydrogen bonds. Okay, good. Okay, next stretch is haloalkanes. I'm not going to repeat the classifications and the namings, okay? We have seen both of these reactions already, the formation of haloalkanes. Notice they all overlap. Now, the important part is that when you want to work out a mechanism, the first thing that you do is to write down dipoles, okay? Halogens are more electronegative than carbon, so this is always delta positive. It will be recurring for every mechanism, okay? First step is to do that so that you can work out the mechanism after. So one point that I want to make is one distinction that sometimes is easy to forget, and it's when haloalkanes do elimination and when they do nucleophilic. So when they react with sodium hydroxide, depending on the solvent in which they're in, they do different mechanism. So sodium hydroxide and ethanol would be elimination because the sodium hydroxide is reacting as a base, while when it's a nucleophilic substitution and it's sodium hydroxide is in water, it will be a nucleophilic substitution, okay? Because it will react as a nucleophile. Okay. Mechanism is always the same. Notice nucleophile to electrophile, and then the bond breaks because carbon doesn't want to have more than 4 bonds. Okay. In the case of an amine, to forming an amine, you have one extra step, but here you can figure it out if you fully understand your curly arrows, and you would be able to work out that there is a positive charge formed. Okay. The one we're practicing the exam practice. Now, one point that, and one nice experiment that you might have done at a school, or that you could be asked, or that you can link it with the kinetic part, this is very nice, is the the rate of hydrolysis. Okay, and here we link it back to group 7, so the precipitate, and as we know that the rate, and remember that for who is studying different type of substitution mechanisms, so here I'm referring to SN1 and SN2 mechanism. This is an SN2 mechanism because there are two terms in the rate equation. Okay, A-level students, remember, second order with respect to like the total order of the reaction, it's second order. Anyway, this means that the rate depends on the substrate as well as the nucleophile. The stronger the nucleophile, the faster the rate. The rate determining step here, of course, will be the breaking of the halogen bond, which means that if it decreases the bond strength, it decreases in rate. Okay, I want you to think about the decrease, the bond strength, how it's related, but not right now. Just whenever if you will have to explain it in an exam question, this will be useful. Okay, this is the second mechanism for elimination. Who is studying elimination 1 and elimination 2? This is an example of elimination 2, because two things that affect the rate determining step. Okay, if you don't know what it means, E1 and E2, don't worry about it. Okay, important, the ozone depletion, the mechanism, but I would rather look at the exam question to try it out, but it's very similar to the radical substitution. Okay, I'm gonna skip through, but please come back to this slide if you want to revisit it and go through it. Try to write it down and write the overall equation, but for now I'm gonna skip through it. Okay, and actually this is the end somehow. Now, this is the point that it's important to highlight. I want you to be able to build or use mine or use the one provided by your school or your exam board to study organic reactions and to do conversions. Okay, it's very important that you realize the connections between different functional groups and how to form one functional group to the others, because in organic synthesis, which is one of the last topics in year 13, this is 50% of it anyway, but you must know, for example, how to get from an alkene to a nitroalkane, so an alkane to a nitroalkane. So you needed to find a connection. So a really nice way to study organic synthesis is literally that you just self-quiz yourself and you look, for example, okay, I'm gonna take alkane and then I'm gonna take another random functional group far away and I'm gonna work its way through it to see the possible type of conversions and organic synthesis. Okay, this is how I would suggest you to study this. And a last stretch here is, well, the summary, the test tube reactions. Here is a nice summary. I'm not going to highlight it now because we've seen some of them already, and some of the tests, they're just relatively simple. Okay, just please or use this note as a nice summary for when you have to do this topic. But the other point that I wanted to make, it's oversimplify the infrared spectroscopy. Okay, like when you study NMR, and if you studied NMR with me recently, we have gone through the summary of the techniques to identify, what is it? I don't have the title of the topic, but to identify functional groups, okay? To identify molecules or structures of molecules. The most important thing you must remember for infrared spectroscopy is that you use infrared spectroscopy to identify functional groups. Don't think too much about anything else. And that there are very common shapes for specific functional group. So don't rely too much on the data sheet when you have shapes like this that are like very easy to identify. Okay, but remember, the most important thing is the infrared spectroscopy is to find the type of functional group that is present. Sometimes you have this, sometimes you have the chemical test that can help you identify the functional group. Then mass spectrometry. I'm not going to go through it now because I think it's exhausting at this point, but the single most important thing to do with it in organic chemistry is that it's used to find the MR of molecule, okay, for structure determination. This means that you're looking at the molecular ion, which is the heaviest one, okay? This is the most important information you get from the mass spectrometer. Then, of course, you can get a little bit of structured information, like the due to fragmentation. And you could have some trick question. For example, why do you have a very small peak that is 1+ in mass? And that is always due to the carbon-13 isotope. Okay, but anyway, once again, because we're talking about structure determination, the most important things are infrared for functional groups, mass spectrometry to find the MR. With these two informations and with the NMR, you would be able to find the structure of any molecule. Okay, this is the end of all organic chemistry. Ooh, maybe a little bit longer than I expected, but I hope that you have a good overview and you revisited and you made a good note of any of the topics that are particularly difficult. Okay, and now we'll look at some exam practice.